I don't know. Uh, do you guys know when is this final project due? Is November 30? Okay, we have 2 weeks. So I'm going to explain today the software. If you have any question about the software, we could have a new session this Thursday. Otherwise, if you don't have questions about the software, we could meet here on Friday, just to see how the project is going. If you are doing a good advance, well advanced in the project, just bring the file. We could check it in this laptop, and I could say if you are doing something wrong or everything is correct, okay? So the problem is we have a flooding problem here. This is a real case. It's close to Waterloo in Cambridge, Ontario. So to control the flooding problem, we are going to construct this dike, okay? So to construct this dike, we have many things, many considerations. The only thing you have to take care about is geotechnical design. And the only part in geotechnical design we're going to solve is slope stability, okay? So let's go through the material properties. We have, okay, this is introduction. This is just to let you know that we are going to use effective stresses, okay, because this is a long-term analysis. So this is just theoretical part, no problem. So, okay, so the idea is that you guys conduct a slope stability analysis to design the dike. So what is design? Designing the dike means this is the level of the soil now, and we have some water incomes, okay? The level has to be controlled, so to control the level of this water, we're going to construct a dike. So the idea for the design of the dike is to define the optimum value for the base width, this one, the optimum value. So you cannot change this one. You cannot change the height of the dike, the top width. You cannot change. The only thing you can change is this one, and of course, this inclination. Okay? So we have 3 different materials. Your mission is to define what is the best material to construct the dike and what is the optimum dimension for each material. Okay? So once you have the optimum dimension for one material, that is not the solution, because the next material could be better or could be worse. We have to analyze the 3 materials. Okay? So first, we are going to use some hand calculations. So the first part of the project is to solve the slope stability problem, considering these recommendations or these considerations. Use the ordinary method of slices to evaluate the slope stability, both on wet side, this one, and dry side. Okay? We have water. So for the hand calculations, we don't have to optimize this. Okay? This is a given value for the hand calculation. Just take this value and calculate, perform the slope stability analysis. Okay? and use material properties of soil 1 and soil 4. So for hand calculations, this is material 1, and this is material 4 for hand calculations, okay? Assume the phreatic surface varies linearly. What that means is we have this water here, we know this value, and we know this value. So assume the variation is linear. Is that real? No. But it's the simplest way to solve it. Okay? Use material properties, assume the phreatic level, okay? Assume hydrostatic conditions, no flow of water, okay? So the solution is the same. For simplicity, select a potential failure surface such that the failure circle is tangent to the hard second lead. So it's something like the failure surface is not going into this material, okay? It's very easy because just consider this material. Everything is dry in moment. Any question about the first part for the project?
Does that mean you don't even have to like really consider the properties of soil 4?
No, you don't have. You don't need it to this analysis. But that is for hand calculations, okay? Any other question about this part? How you define the failure surface. I'm going to explain how the software defines the minimum factor of safety. What you are doing is just one iteration. Let's assume that you could take 1,000 surfaces. You could take many different locations for the center and take different radius for the circle. So you could get different surfaces, different factor of safety. One of those 1,000 factor of safety is going to be the minimum. That minimum is going to be the critical surface. Okay? But for this analysis, for hand calculation, just select one surface and that's it.
Isn't the surface should be underneath the document?
Say again?
The surface should be underneath the document, right?
Yeah.
This is doing two documents.
For the surface, let me put this. Just to consider to simplify the problem, don't take a failure surface like this, okay? Because you have to consider now this material. So just consider one surface like this, okay? Doesn't matter the surface you choose, it's going to be just to demonstrate that you are able to solve the problem by hand, okay? That part is easy, but the only consideration and the difference with the assignment is that now we are going to consider effective stresses, okay? Effective parameters. Is that clear? So the factor of safety, the formula for the factor of safety is different, but this is still easy, don't worry. Okay, so now we have to solve the problem using rock science slide. Now we are going to complete a more detailed analysis for each soil type, 1 to 3, So the idea is that now, for the software part, we're going to consider soil 1, soil 2, soil 3, and for this part, we're going to consider soil 4, always, okay? So we have 3 different materials. You don't have to combine the materials in this part of the embankment. Just use one, and after that, repeat the exercise, just changing the material. So the idea is that you have, as I told you before, you have this maximum B. That is maximum. So you have to optimize the design. That is the point. Now, for these materials, we have to consider this, the possibility that the surface go into this material. So we have to consider a bigger problem. Okay? Okay, but for this analysis, we have to, we have to perform the analysis in this direction and this direction. So that means for the wet side and for the dry side. Okay, and determine the phreatic surface using the flow mode. Okay, we're going to explain that. Conduct the slope stability analysis for the wet side and dry side. Okay. Any question about what we have to do? No?
How do you determine the angles? Which angles are we talking about?
We are going to show, I'm going to show you that in the software, okay? So this is these are the dimensions. So we have the length of the dike is going to be 350 meters. What that means is long enough to be considered just a cross section, and assume that that cross section is representative for the total length. So what that means is just take one cross section to the analysis. Maximum base width 37 meters. This one. Top width 2.5. The height of the dike 7 meters. Okay? And the water here is 0.75 meters. Okay? Now, how do we know the height of the... Okay, here we have the dimensions were designed for a 25-year storm frequency, a normal ground elevation of 200. We need this value. 0.31. And for the water is 263. Okay, so now we have everything. Okay, we don't know the slopes, but now the parameters.
What is the length? Where's the length?
Just assume that this is the dike. So just taking one cross section is enough. Okay. Okay. Any question about the dimensions of the problem? The geometry is completely clear. The geometry. Clear. Okay.
So less than 37, we can look at it.
We are going to start with this dimension. We need a dimension to start. This is the starting point, okay? Now, the properties of the materials. So we know this is going to be effective. Here, just to simplify your life, assume this is gamma total, okay? Gamma total. I'm going to explain that inside the software, okay? And we have cohesion and friction, and we have intrinsic permeability. Do you guys know what is intrinsic permeability? No? Do you guys remember hydraulic conductivity? Yeah? Okay. In hydraulic conductivity is the parameter we use to relate the flow discharge with the head in the Darcy's law, okay? With the variation of head, of hydraulic head in Darcy's law. But that hydraulic conductivity is a parameter which is considering the soil properties and fluid properties. So to avoid that, we could use intrinsic permeability, which is a property just for the soil, okay? But for the software, we need hydraulic conductivity, which is equal to the intrinsic times gamma for the water times, this is called dynamic viscosity, okay? So this is the unit weight for the water, and this is dynamic viscosity. Okay, so we know this parameter, now we need this one and this one. How do we get that? There are many sources. Just on the internet, I got this website. So for different values of temperature, you could get a specific weight for water, and in the same way, you could get dynamic viscosity for water. Just choose a temperature value, whatever you want. Just be sure that your state in your project, I'm choosing this parameter, the unit weight for the water at that temperature is this, the dynamic viscosity is that, and considering this intrinsic permeability, I'm calculating these values for hydraulic conductivity. Okay, we need those values. Any question about that? Awesome, good. So now, assume that is gamma total, and we are done. Let's start. So, in the computers lab for civil engineering, you have the software installed in the computers. So, the software is called Slide. Okay? You see the name? Slide 6.0. So I'm making a video with this. Whatever we are doing here is going to be posted in a video in YouTube maybe. So the idea here is we have this. This is the initial screen for the software. So Slide is performing a limit equilibrium, okay? It's not finite elements, it's not finite differences, it's just limit equilibrium. So for Slide, we have many options. We could consider the water as a water table. We could consider the water as a RU factor, water table. we could analyze, the water as transient analysis. Do you know what this means? Transient analysis? Do you remember the flow nets? That is a transient analysis. So if you see this problem, you could perfectly solve the problem by doing the transient analysis to find the water position. Okay? So you could do that with the software. Or we could use finite elements. But this is just for water, for groundwater flow. For one groundwater flow, we could use finite elements. The rest of the software is working with limit equilibrium, okay? So the idea is, depending on what option are you going to use, we could define the geometry in different ways. So my suggestion for you is to consider the real coordinates for the problem. So if the position for the soil is now, this is the ground level, is 257.71, just consider that for the coordinates. So let's start by doing this. Let me clear this. So we have this problem, and we are going to design the dike. Okay? For hand calculations, we don't need to consider the soil below the line. But now, how do you know the thickness you have to consider for this soil? You don't know. So my suggestion is to use at least the same height for the dike. So if this is 7 meters, just assume at least 7 more, okay? So if this is 200, is that 271? 50, 257, yeah. If this is the value, just for simplicity, take the reference level at 250. Okay? And now, because we are going to perform flow analysis, we have to consider this boundary far away, but far away means far enough just to guarantee that these parts of the model are not affecting this part. So just my suggestion for you is that if this is going to be 37, just take half of this distance. Something like 18 meters could be. From here to here. Okay? Okay, we have the geometry. Any question? No questions. So, what is the coordinates for this point? Which are the coordinates for this point? Let's assume these ones are 0 times 0, x 250. Okay? So I'm going to do that in the software. Exactly that. Okay, for this software you have menus, file, just to control it's exactly the same as Windows, as Microsoft or other softwares, just to control the file, edition, the view, just to know how do you want to see the interface. The project settings, the analysis is to define the project settings, but first we are going to define the boundaries, okay? So to define the boundaries, we are going to use this first icon. Okay? Add external boundary. This is the first part. So how do we add the external boundary? We have over here in the left, in the right, sorry, over there we have this interface to introduce coordinates. Okay? So we know the coordinate for this point, 0.250. Okay? Now, zero comma 250. Okay, now, what is the coordinate for this point? Is 73,250. Okay, we have the first line. This is this part of the model. Okay, now the same for this point. Coordinates. Coordinates for this one, this one, this one, this one, and this one. We don't need to define the coordinate for the water. Okay? Just define the coordinates for this part. Okay? So, for example, for the next one is 73, 277, 0, oh. So we don't know exactly this one. Let's assume that this one is like this. 80. Okay. So what I did was just define this one, this one, this one, this one, this one, and this one. I haven't defined these ones exactly, I mean, not real coordinates. These are not real. Just to create the model very fast. But now, we have one addition element here with one tool, which is with the right button, we could select Move To. With this option, we could move the point to real coordinates. And you could change the coordinates. That is going to be important when you are going to modify the slope of the dikes, okay? If you are going to modify the slope, we have two options. This is one option, modifying the coordinates. So for this option, what is the real coordinate for this one? So we know that this one is 72, this one is 36.5, this is 2.5, that means this one is 37.75. And the other one is okay. So Move To. Okay. What is it? The key here is for this part is okay. Okay, so let's move this point. I gave the option move to. And move to. Okay, that is the real geometry. Okay, we have the external boundary. Now we have to define the material boundary. So, material boundary. This is the second option. Once you define the external boundary, the rest of the commands are you are able to use the rest of the commands. Otherwise, you cannot. Okay, this is the material boundary, just connecting these 2 points, and that's it. Now we have the geometry of the problem. Okay, let's define materials. So this menu loading, we are not going to use it. This one support, we are not going to use it. Surface, okay, we are going to use it, but first let's define materials, properties. So define materials. Here we have the option to define up to 20 materials. The first one, if you want to change the name, just write down soil 1. Okay, you could change the color if you need. If you want, let's say you don't like yellow, you like pink, I don't know. So the unit weight, please let me know the unit weight for soil 1. Nobody has the material properties. 18? Okay. So you see here we have 2 options, unit weight and saturated unit weight. You see? But we cannot use saturated unit weight here. Why? Because we are not defining water table. So let's go to this part. We have the external geometry, and we want to define the parameters for the analysis. Okay? So when we want to define the parameters, we have to define first the project settings. Project settings is giving you many options. The general one is defining the direction of the analysis. This direction of the analysis is allowing you to define if you are analyzing wet side or dry sides. If you are going right to left, that means you are going to analyze dry side. Left to right, you are going to analyze wet side. Okay? For the first one, let's analyze dry side, right to left. Okay? Don't modify this data output. We don't need it. And we are going to use metric system. 4 times we are going to use days, permeability, meters per second. You could change it if you need it. For the methods of analysis, you could define Bishop, Corps of Engineers. There are 2 methods. Morgenstern, Jambu, simplified and correct, and low Kafia. Oh, I don't know that method. You don't need it. Just select Jambu, it's okay. Select Bishop, it's okay. Spencer, maybe, it's okay. Yeah, you could choose whatever you want for the methods, but these are the most common methods. Bishop, Jambu, Spencer, okay? Sometimes you could use Jambu, correct. The only difference, do you know Jambu? So what do you know about slope stability? It's basically the if you want to analyze this problem, so you can divide the surface using this slice, okay? So every method has defined a different way to calculate forces between these slices. So the only difference between methods is how are they considering the interaction between slices. Okay? Some people is considering shear stress between slices, other people is not considering shear stress between slices. So that one example of that is Jambu, simplified, is not considering shear stress between slices. Okay? But Jambu corrected method is giving you the option to consider shear stress, which is more realistic because you are actually, you have, okay, when the slope fails, it's not failing like every slide apart, no? It's failing like a continuous method, continuous volume moving. So just define here, let's use Bishop, Jambu, don't use correct, and Spencer. Define these three methods, okay? Now for groundwater. For groundwater, we have many options, I told you before. But we have water surface, which means I'm going to define inside the dike, I'm going to define the water surface. But we don't know the water surface. So that option is not realistic one for this problem because we don't know the water surface. RU coefficient is the simplest method, but it is maybe too simply. The simplification is too much for this problem. We cannot use RU method when you are considering flow between upstream and downstream. You cannot use RU. The grid total head, the grid pressure head, the grid pore pressure is when you have the solution for the flow net. Okay? So you have the solution for the flow net and you decide to use it. For example, if you perform the analysis using finite differences, and now you want to use that flow net, so you use these options because you know the solution for that grids. But this one, the last one, is the one we are going to use, okay? A steady state, finite element analysis, okay? When you define a steady state, different menus are going to be displayed in the software, okay? So let's say, okay, let's go back, analysis, project settings, groundwater, let's change this to water surfaces. Okay, this is what we see at the beginning. We saw this interface, okay? Be careful with this part of the software, okay? When we change the analysis, the project settings to groundwater steady state, you see this new menu? This one is allowing you now to change between slope stability analysis and groundwater analysis, okay? If you go to groundwater analysis, you are not performing slope stability. You are just analyzing the flow of the water, okay? But that option is just when you have the analysis, when you have a steady state for the groundwater, okay? If you don't have that, the only menu you have, if you don't define the steady state, the only option you have is to perform slope stability, okay? So now, let's say we are going to use steady state. We are not going to use transient. We are not going to use statistics, random, design, advanced, anything else. So for these project settings, the only thing you have to define is general. Be sure about the direction of the analysis. Methods, Bishop, Jambu, and Spencer. Groundwater, a steady state, finite element analysis. That's it, okay? Okay, so now we have these properties. Okay, now let's go back to properties of the materials. Define properties. So you see, for finite element analysis, we don't have the option to use saturated unit weight. Why? Because there is something called water retention curve. You know that? Water retention? Okay. So the water retention curve is showing you the relationship between permeability or hydraulic conductivity and matrix suction. But that is a little bit more complicated to understand at this level. For your technical engineering too, don't worry about this part. Just simplify your life. Use unit weight, the last one, and let's, the weights you are given, use it as unit weight and as total unit weight. And for the analysis, let's use finite element analysis. If you are using, for the analysis, you say, no, I want to use water table, water surfaces. Okay, I want to use water surfaces. The first thing you have to do is to define the water surface. So let's say from here to here, for example, this is my water surface. I'm going to affect every material. And now I'm going to define the properties of the material. I could define saturated unit weight. Okay? But we are not going to do that. It's a little bit more complicated because we have to define this curve for the materials. Okay, let's go back. Analysis, project setting, groundwater, steady state. Okay. Okay. Okay, let me know the materials. The first one, soil one. Let's change the color. You don't like that one. 18. What about the cohesion? (15 kilopascal). Okay, you see the units are exactly kilopascal. Don't worry too much about that. The friction, 28. Okay, 28. So you see here we have many different options to define the failure criteria. I told you before in one tutorial, more Coulomb is just one model, and we have many options. But more Coulomb is the simplest one, and is the most used in practical life. So use more Coulomb. But there are many other options. Actually, if you want to perform slope stability for short term, you could use undrained resistance. You see, this one is using basically CU, okay? But now we are going to use more Coulomb. So this is my first material. Here I'm defining material properties from a stability point of view, no hydraulic point of view, no hydraulic properties for the materials. Why? Because we are in this menu, okay? Slope stability. If you change the menu to groundwater, now we could define hydraulic properties. So we go to the first one and we define the permeability, okay? We have to calculate the hydraulic permeability considering what I explained before, but let's assume that is the value, just to assume that is the value, okay? Let's go back to slope stability and define the rest of the materials. Material properties, soil 1, soil 2. Okay, what is the unit weight for soil 2? 19. Eight kilopascal and 29. Soil 3. 19,530. And soil 4. Nineteen, 15, 30. Okay, now I have the materials defined inside my project. Okay, you could save the project before. Okay, save the project. Let's say this is trash for me. Okay, I'm not going to use it. And this is material properties. So how do I assign the material properties? This is the first, this material here is going to be soil 4, okay? You see that? Now you have the materials. This one, soil 1, okay? Now you have assigned the materials, okay? Any question? Once you finish the project, the only thing you have to do is create a copy of that file, open the file, come to the material properties and say, change the material to soil 2, and run again. Do the same and change to soil 3. Okay? Now, this is just geometry and materials. Let's go to, this is soil 1. Okay, let's go to water flow. Okay, so for water flow, we change the menu. Over here, we change the menu. And now we have to define the parameters for the groundwater flow. So the first thing we have to do is to create a discretization of the problem, because we are going to use finite elements. Okay, so let's go to this command, match app. You could define the number of elements you're going to consider for the analysis. 1,500 is not too much. If you want to change it, it's okay. At the end, this is a very simple problem. It's not going to create any complication if you change the value of the number of elements. Okay, you could change the type of elements from 3 nodes to 6 nodes to 4 nodes. Do you know what that means? Okay, you have this. Okay, let's do it. We have to discretize this problem. So we have many options. For example, let's do it like this. Okay, each element here has 4 nodes. So this element is 4 nodes element. Now what happens if I decide to use this element? It's 3 nodes element. That is what that means. What kind of elements? For this problem, which is very simple, doesn't matter. You just choose three nodal elements, is going to be okay. Okay? And let's improve the discretization and discretize. Okay. Now you see these small red crosses, these are the discretization, okay? After that, we have to define the mesh. You see? Let's remove the mesh. Let's do it again. Discretize, mesh setup, discretize, okay? And match up. This is the match we are going to use. So now, let's change this color, which is not. Okay? Now we have to define the boundary conditions to perform the groundwater analysis. Do you know what the boundary conditions, what that means? So we know that we have water here. And we know that we have water here. Okay? The water table, no. Yeah. Yeah, that is one option, but that is for the geometrical considerations. For boundary conditions, we have to explain, to give to the model the values for hydraulic head at some points. So do you remember hydraulic head? So if the water is at 263.3, what is this? This is total head. Okay? So that is one boundary condition. We have a total head of 263. And we have a total head which is 0.71, and we have plus 0.75. This is the other value for the total head. Those are the only conditions we know. We don't know anything else about the model. Okay? As we don't know, we are going to define, as you see, the first consideration for the software is, you see this interrogation, the symbol, interrogation? What that means is, I don't know the boundary condition. The software is telling me, I don't know the boundary condition. I'm going to tell the software, I don't know the boundary condition. You have to solve it. Just define the total head for the points I know. I know this point, I know this point, I know all these points. And I know these points. The rest of the model, I don't know. Just solve it. So, to create this condition, we need one node here at this point, 263, and one node here at 0.75. So this is something like 8. How much is this? Okay? So we are going to assign the value for the head, the hydraulic head. So we are going to use this command, set boundary condition, okay? Set boundary condition is giving me the option to select between total head, zero pressure, nodal flow rate, and other options. The only one we know is total head. We don't know anything else about the model. So we are going to select this value at 263.3, okay? This is the total head I'm going to assign. For these points, for all these points, $263.3, and let's say I'm going to assign the boundary condition, boundary nodes, okay, for the selection mode. I'm going to use boundary nodes. So I'm going to assign the value for the total head for these points. Enter. So now we have the water, but we have the water, we don't have the water in this part. So we have to define also for this part the water. Okay? So you see the problem here? Now, I need to define exactly one node if I don't have this node at 263.3, I'm going to have that problem. So water is going up or down because the software is going to the next node. So we don't have the node here. So we need to go back. So this one is not going to allow me. Let's go to slope stability. Remove this discretization. How? We could do it here. We could remove the discretization here, the mesh, and reset the discretization. Go to slope stability and define one node at this point. So this is a tricky part because we have to define the coordinates for this node. But the software is allowing me to use the zoom. So, and I know here in this part of the screen, I don't know if you guys notice this. These are my coordinates. Okay? So, because I'm a practical engineer, I don't want to waste my time doing more calculations for that point. I'm going back up to 263.3. We have one node. The next node, at this point, we do the same. We add one node, one vertex. You see the command here. And the next one is going to be at 258.46. Okay, now we have the nodes. Okay, we have the nodes. Now we know that this is the node when I know the total head, and this is the node when I know the total head. Okay, so let's go back to groundwater analysis, discretize again. Okay, so for this one, now you know, now you see there is one node here, and it's going directly to that point, the discretization. So create the mesh, and now we have solved the problem for that part. But you see, these nodes somehow are defined with total head of 263. That is not correct, because we don't know the total head for those points. So we assign the unknown here, and we assign this value, and this value as unknown. The only values we know are these ones. Okay, close. And now define the same for the downstream. So now the total head is going to be 258.46. And this is the point. So these are the points. Be careful, because if you see here, I select some internal nodes. If you select internal nodes, the total head is going to be applied to those nodes. If you want to avoid that problem, just close here, go here and say, don't use boundary nodes, use external boundary segments, okay? And now, You see? Oh. Okay, now we have the definition for the groundwater. Any question about this? Okay, next step. We have to be sure that we are assigning the hydraulic conditions, okay? Don't forget this part. For soil 1, just define the hydraulic permeability, conductivity for every soil, okay? And next step, just compute the analysis with this calculator icon, okay? Compute the analysis. To display the results, the analysis is already done. To display the results, we use this icon, which is going to open a new screen. It's not the same one. This is the analysis. So we have here the total head, pressure head. So to display, the options to display are here, we could say display options, contour options. So fill and lines. I like using lines because that one is allowing me to see the materials. Okay, now we know this is the water table, and that is the input for my slope stability analysis. Okay, this is what you have to do. As long as the discretization, the geometrical conditions, and the nodes are the same, you don't have to run the analysis again. If you modify even one node, you have to perform the analysis for groundwater again, okay? So these are the results. This one are not the, you are not going to use this screen for anything, this result for anything. The software is doing the work for you. So now we have the groundwater analysis performed. Let's go to slope stability. Okay? So for this one, we have now everything we need. The only thing we are missing is the definition for the grid. So this is the option, auto grid. Okay? But before that, we have to come here to surfaces. And here we are defining the kind of surface we are going to analyze. For surface options, you could see circular surfaces, non-circular surfaces. We are going to use circular surfaces. And just sometimes, if this material is, for example, rock, you have no possibility to go inside. The failure surface has no possibility to go inside the rock. So the software is allowing you to combine the surface, doing something like this. Sometimes you are defining a circular surface, which is creating this kind of reverse condition. So we need to create this kind of surface. It's something like in this. For example, in this case, okay, you could do this for hand calculations, it's okay. But for real life, this is not the real life surface. The surface is not going back. So you have to keep the surface going up from this point. So the software is allowing you to do that. But anyway, the only thing you have to consider here in surfaces is to create this auto grid. With this auto grid, you're basically what you're doing is your problem. So someone asked me before, how do I select the surface? So you have one option to select the surface, but there are many other options. Okay? This auto grid option is giving me the option to define a big space with many options for the center of this circle. Okay? So what I'm usually do is use 100 by 100. Okay? And it's done. Now you have the surface, you have the grids, and we could perform the slope stability analysis with this icon. With this icon, we could display the results. And that's it. That is one slope stability. Okay? Now, this is the first this is exactly the same result I'm showing in the other part. This is the result. This one is correct. Everything is correct here. But now we know that this slope is the initial slope, and that is the point we have to optimize. So one option is to reduce the width so I move the point from here to here. And now my new slope is this one. And the next one, this was the first one, this is the next one. This is the other one. You could see 43 degrees, and my factor of safety is more than 1.4. So, and for the next one, I do the same for the other side. And now, the width of my, let's open the real solution. So for the final solution, we got something like the width of the dike is going to be around 17 meters. Okay? Yeah, this is already record in the video. But anyway, guys, I know this using software first time is not easy. If you need help, we could meet here Thursday and Friday to solve it, okay?
Good morning. Can I ask a question about the assignment? For this question, can we say this angle is equal to this angle?
Ah, okay. list of this.
Sure.